Okay, today we're going to start our next chapter, chapter 16, and what we're going to look at is what nuclear reactions are all about and how to calculate them and so on. So our first lesson, first of all, is just getting used to new notation and things of how we're going to use the periodic table a little bit differently than you might have in chemistry. First of all, we call it nuclear physics and nuclear reactions because we're dealing with what's happening to the nucleus of the atom. In chemistry, quite often, we mostly pay attention to the electrons, because it's the electrons that determine the bonds and how the chemicals react to each other and so on. In nuclear physics, we're worried about just the nucleus because it's the nucleus that's determining what the element is and how it's going to disintegrate or give off energy or absorb energy and so on. So first thing we'll do is let's make sure we know what the nucleus is made of. We call them nucleons, so it's basically anything inside the nucleus, which is basically protons and neutrons. So remember, a proton is positive, so we write it as P plus, and we know it's the same charge as an electron, so it's a positive elementary charge, so positive 1.6 to the negative 19.
Santana Miller to the office, please.
And we know the mass of a proton is 1.67 to the negative 27, and so it's the atomic number on your periodic table that's telling you how many protons. So if you look on your periodic table, and we look at something like sodium, we see that sodium is 11. So we say that the atomic number 11 is based on how many protons there are. And then neutrons are the other particles. They're neutral. They have no charge. The mass is almost the same as a proton, just slightly bigger. And the total number of neutrons added to the total number of protons gives us the atomic mass number. So if you look at sodium, we have 11 protons, so sodium is number 11, and if we normally would have 11 neutrons, that would give us a total mass of 22. We have 11 protons, 11 neutrons would give us 22. But when you look on your periodic table, you can see the atomic mass is about 22.99, so it's almost 23. So what that means is, typically sodium then is actually one extra neutron. It has one extra neutron and still just our 11 protons. So when we write these things, that's how we're going to do it. So the top number is the number of protons, the bottom number is the total number of particles. And actually, I think I just said that backwards. I did. So let's go back to the previous page. I wrote that backwards. It actually should be 23 and 11. So 11 is the protons, 23 would be the total. Okay, so let's look at this one. So if we have 15 and 7, so that's for nitrogen. So nitrogen is 7 on our periodic table. So we have 7 protons, and 8 neutrons would give us 15. So we write it as 15, and we name that as nitrogen 15 or N15 for that chemical. So if we look at 2311Na, that's what we just talked about. So 23Na11, so it's 11, which means it's sodium, and 23 would mean we have 11 protons, and then we'd have 12 neutrons. And that's it. So in chemistry, when we say if a chemical has more electrons or less electrons, we call it a positive or negative ion because it's affecting the charge. But in this case, if we're only gaining or losing neutrons, the charge doesn't get affected, but we still get a different mass and things like that. So we call these isotopes. So an isotope is when you have different numbers of neutrons. And isotopes will be similar in terms of chemistry, but we do need to worry about it in terms of the nucleus being a different size and a different mass. So for example, if we look at carbon in nature, carbon is 6, so we should have 6C, and it actually comes, we can find it in abundance most often, it's 6C12, which is normal. Right? If we have 6 protons, 6 neutrons, we'd have 12 total, and in reality that happens almost 99% of the time. But there are some cases where it's either missing a neutron, so we get 11C6, or it's got an extra neutron, which is 13C6, and rarely as well it might have an extra 2. So sometimes it has an extra 2 neutrons. So you can see 98% of the time it's carbon 12, 1% of the time it's carbon 13, and then rarely does it happen as the other two. But if you think of these as being sort of a weighted average, if 1% of the time carbon is actually one extra neutron, that's why when we look at the molar mass of carbon on your periodic table, it's 12.01. So it's mostly often 12, but 1% of the time it happens to be one extra, so that's why we're getting that little bit extra weight to it. So the masses on your periodic table are based on averages. It's not what's actually always going to happen. So you can see here, so carbon is close to 12, but we get a little bit extra, so that's why we call it 12.1. So that's an average mass. The number of neutrons will affect the stability of the nucleus. So if we have it as 12C6, we'd say that's a stable nucleus. That means not much is going to change. If all of a sudden we have way more neutrons or way less, then we say they're unstable, and that nucleus is it's likely going to decay and release radiation. So that's why a chemical like radium or uranium or plutonium, things like that, they are radioactive because the number of neutrons is typically way too many, so they always want to try to get rid of them to balance things out. One more calculation in terms of mass is masses of atoms are usually given as atomic mass units, which it's not part of the metric system, but it makes more sense because we're not dealing with kilograms. The mass of a proton is really tiny. It's to the negative 27 kilograms. So just like we do with electron volts, it's just a simpler way of doing it. So if we have a neutral carbon atom of 12, we would say it has 12 atomic mass units. So that means one unit would then be 1/12. So one atomic mass unit works out to be 1.33 to the negative 27. Okay, and actually I think that number is wrong. If you look on your periodic table, it is 1.66, so there's a typo here. So it's 1.66 to the negative 27 is our atomic mass unit. So then if we divide the mass of a proton by an atomic mass unit, you can see we actually get a little bit more, and we divide the neutron by atomic mass unit, we get a different number, and if we divide electron, we also get a different number. So these are the actual atomic units of a proton, neutron, electron. So if you actually did those calculations for something like lithium, we'd have 3 protons, so 3 times the 1.007, and typically lithium quite often has an extra neutron, so we'd have 4 times that. Average it out when it has 4, when it has 3, and so on, and that's the number that's on your periodic table. So that mass number may or may not be exact depending on whatever type of situation it is. We know that nucleus, like if we think of a nucleus as being positive charges for the protons, so let's suppose we have something like helium, we have 2 positive charges, and we'd have 2 neutral charges, 2 neutrons. So we know that those 2 positives are going to want to repel, right? If we have 2 electric charges that are the same, they're going to want to push apart. So the question is, why do they stick together then? What's keeping these things together? So if the electric force, which is quite strong, is trying to push them apart, then we have to have something holding them together. So we call that a strong nuclear force. So the strong nuclear force is pulling them together, the electrostatic force is pushing them apart, and if it's stable, then that means the nuclear force is kind of holding its own and it's winning the battle. If it's not, if the electric force is bigger, then we're going to start losing neutrons or whatever, and it's going to start to decay. So as long as the nucleus is stable, we need energy to get those things apart. If we're going to add these things together, then there's always going to be this energy. So Einstein basically did some work on this area, and he found out that the masses of the neutrons and protons when they're separate was actually bigger than when you put them all together in a element. So if you think about that for a minute, it's kind of like having Lego pieces. So you have 10 different Lego pieces separate. They have a certain mass. You stick all 10 of them together, and if you weighed it on a scale, it'd be the exact same mass. But what Einstein found out is it was different. The 10 Lego pieces separate, to start with, had more mass than when you put them together. So they were losing some energy. So what he thought then is there's some energy that's being wasted to stick these things together. So, which kind of makes sense. If you took 2 pieces of metal and tried to stick them together, you're going to need to use some of that energy, welding or whatever, to make it work. So what Einstein then figured out is some of those masses, parts of the masses, get lost as that mass gets converted to energy. So the most famous formula in physics, E equals mc squared, is that formula to calculate how much energy is produced based on how much mass is being lost. So you're going to get some calculations on mass defect, and basically what we want to do is just figure out how much mass is lost when we put these things together, and then convert that to energy to figure out how much energy was used in the system. So it was due to this that nuclear bombs and things started to get developed afterwards. So Einstein didn't develop the bomb, but it was his idea that mass can be converted to energy. So what they found out is if they take plutonium that's quite unstable, break it apart, there's energy that gets released, and that energy is then what is the effect of the bomb. Okay, so let's do this last example. So we've got zirconium-93, and it tells us the mass is 92.9 atomic units. So the question is, what is the mass of just the nucleus? So what we have to do to get the nucleus is we know that zirconium is 40 on our table. So we have 93 ZR40. So that means we've got our mass that they gave us, 92.9, and I'll just leave it at that. We have to actually subtract 40 electrons, and the atomic mass of electrons on that previous page was 0.005486. So we just have to subtract that to figure out what the mass is with just the nucleus, which it turns out to be 92.88, rounded off. So now what we want to do is we know that's the total end energy, so now we want to figure out what the energy is before. So we have 40 protons plus 53 neutrons to give us a total of 93, and that energy, or that mass plus some sort of energy, is going to equal to 92.88. So we just have to calculate that. So 40 protons, a proton is 1.00727 on the previous page. 53 neutrons was 1.00866, plus some sort of energy equals 92.88. So we do this math, we calculate this out, and solve it for energy, or solve it for mass, sorry. So that means the mass that ends up being left over ends up being, so if we go the 40 times 1.007 plus 53 times 1.008, we subtract it from 92.88, we get an answer of 0.86577 atomic mass units, and let's times that by the mass of one atomic mass unit, which is 1.66 to the negative 27, and that gives us 1.437 times 10 to the negative 27 kilograms. So it doesn't seem like much, but it's close to like half a proton or something like that. So that's the amount of mass that was lost in the transfer. So then Einstein, we can use his formula to figure out how much energy that is. So take that number and times it by the speed of light squared, and we get a total mass of, or sorry, a total energy of 1.29 times 10 to the negative 10 joules. Which still doesn't sound like a lot, but if we change that to electron volts, or divide that by 1.6 to the negative 19, we actually get 809 million electron volts, or mega electron volts. So one atom of zirconium, you can see it's 800 million electron volts. So that is somewhat significant amount of energy. So you can see why one atom of plutonium is going to release a significant amount. So if we had a big block of it like they put in a bomb, then we got billions and trillions of joules of energy that gets released. And that's it for this topic.